another very important background that you need to recover in case you don't remember it, that we will use in this course, is the concept of linear differential equation with constant coefficients. That is, you need to be able to understand and recognize a differential equation of the form x dot equal to ax, where in this case x is a continuous function, differentiable function, from, for example, R to R. A differential equation is a relation that relates functions and their derivatives. In this case, derivative with respect to times. As example, for example, if you have the function x of t equal to cosine of t, then you know that x dot of t, that is the derivative of this function, is minus sine of t. Okay, so when we are trying to solve a differential equation, we are looking for a function. When we are trying to solve a differential equation of this type, we are looking for a function x of t such that this relation between the function x itself and its time derivative is satisfied. For example, you will know about your system theory and control theory courses that you know how to resolve such a linear differential equation. You know that the solution to this differential equation is what's called the exponential. That is, if you take x of t equal to e to the at x of 0, okay, where by this we means that x at time 0 is equal to x of 0, then this expression for the x of t solves this differential equation. This is very easy to be proven. You know that x of t is equal to a times e to the at x of 0. Because the derivative of the of e to the at is a times itself. And if you substitute it back, you get a e to the at x of 0 equal to the a times e to the at x of 0. You see, check, this is satisfied. That is, this expression, exponential expression for the function f of x of t, indeed solves this differential equation. And this is background that you should know very, very, very confidently. Now, another thing to recognize, and you will have seen it in your control courses, is that this generalizes to multidimensional systems. That is, even if we take x dot equals to ax, where x is, for example, some vector in Rn, but can be a finite dimensional vector, okay, then the solution of this differential equation generalizes in the same way as the scalar case to the so-called exponential matrix exponential. That is, we know that x of t is equal to the e to the at x of 0. And in this case, we need to use the definition of matrix exponential. That is, by definition, the exponential of a matrix is another matrix, the same dimension of the matrix you exponentiate, which is just the identity matrix plus B itself plus b square over 2 plus b to the n divided by n factorial till infinity. So compactly, summation with I from 0 to infinity of b to the I divided by I factorial. And you recognize this is exactly one of the definition of the scalar exponential, which generalizes to matrices. So for this course, you need to recall the fact that whenever we see a differential equation of the form x dot equal to ax, then the solution is something like x of t equal to e to the at x of 0. A result that you should know from linear system theory, but you should study again and commit to your long-term memory in case you don't remember this.